Okay, my friends, we're going to do a sort of a deep dive into particle physics, because a lot of you have been with me for long enough that you know my dipole electron flood theory, DEFT. And it's now sort of being accepted. It works. It works fabulously. Now, I got this today about the Higgs decaying and all that business. They're talking about the Higgs boson. Higgs boson goes back a long time. 2012 is when they actually claimed to have seen this. Now, I've been following this very closely. Fermilab and CERN and all the rest of them. And I'm going to show you what I have found, because I'm not just talking. I have evidence to support the things that I'm talking about. Higgs fields, particles, the photons, the muons, you know, let's just get into it. And for me, it's going to be fun, because I'm going to go back to 2012 and see exactly what they say about the bosons, the Higgs boson, and how, well, let's go through the whole thing, because it's evolved, just as everything has. And I think they're getting closer, but they still want to throw in some fancy little parts. And there is no fancy parts. There's a black and a white. That's it. Okay, my friends, I don't want to be disrespectful, but what is in this article sent to me by my friend Marilyn today, it was just brand new right out, is about the Higgs decaying to muons and anti-muon pairs, and then they come down to fermions and quarks and all these different, they throw all these little terms in, and they think they're all different particles. They're not. They're not. They're made out of the same particles. These two, the black and the white together. And they've seen them, and I'm going to show you how they've seen them and how we've seen them in our experiments. Very simple, very easy to understand. All right, it's extremely simple. Every atom, starting with hydrogen going up, consists of a black center core. It's all the dark matter, and it is dark matter. And then around that is all the glowy little particles. And the closer they are to the core in these levels, the tighter they are held. So blue, when you pull it, you really got to pull it off of there. And blue has a lot of energy. Green, mediocre. Red is just wobbling along. And there is only two particles. There's the ones that make up the glowy ones, and there's the black one. And the black one never changes size, ever. That's it. There's only two things that exist that I can determine. And that one has no mass. I don't know why. I can't put my finger on that one. And it gets huge, and it can get small. It can get so small, we can squirt it through a Venturi, where this one will not go. And there's more to it than that, but just think about it this way. This one, it never changes, ever. It's never going to change size. You can't squish it, you can't expand it. It's the same size, and these two together, held together, make up what I call a dipole electron. Yes, a dipole. Electron's not just one. It is this glowy part, but it's held together by the black part. And the two of them together is the strong nuclear force. Those two together, when they're held together, they're held together. And the smallest, well, let's slow down here. We'll go through piece by piece. What we've got here is these are the particles. That's the only particles that exist. There's a black one and a white one. They can be separated. I never thought that was possible, but it is. They travel together in different energy states. Red to green to blue, really rocking. These are what they call gluons, and they agree. Gluons are the dark and the white one. And then the photons, and we could show this. I will show you these. They've seen these particles here, and they've seen these. They just didn't realize these are photons. And let me show you what they have seen, and then you can make your own determination. All right, so this was just after they discovered the Higgs. This is 2013, February. So this is just starting into 2013. And these were the particles that they were showing from Fermilab, and they were obviously the same particles we found. The same exact particles. That's the ones from the... And then we were able to split them, which is to create electron showers and sterile muons. That, and accelerating the light, it was all, it totally went against mainstream physics, and it wasn't well accepted. Let's just go with that. All right, here's what happens at CERN and Fermilab. They throw big, huge chunks, to me, which is a proton or a neutron, bam, head on, going around, 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 and boom. We shoot light with a laser. And this, we never get anywhere near these size. They get all this stuff, and then they dig through it thinking that there's all different size particles. There's not. There's only two, which is the dipole electron, and they can get into bigger pieces, into X pieces, which are huge chunks. They can be the tiniest little bits. And they can have different energy levels depending upon how you pick them up. Now with the CMOS that they have just started using, they're getting some very, very good pictures, but it's still debris. We started with light, so we started in this range right here, so we didn't have to dig through any of the other big stuff. Okay, so we're going to be talking about Higgs and Higgs fields, Higgs bosons, and all that, because there's some brand new research about it they're talking about, and they're getting close. But again, these are the only two particles. They can be separated, and they certainly want to get back together quick. Now, this is what a photon looks like. It's two dipole electrons back to back. We were able to force that through the Venturi and separate the black and the white, which is pretty astounding, really. The muon is the black part. The electron, neutrino, is the white part. That can go into showers. And the black star just will not go through, but it instantaneously jumps back to the white to become a particle again. This is what's... I'm going to show you some Higgs bosons, and you make your own determination of. This is what we have for Higgs bosons. Those are serious Higgs bosons. Now, the key here is they are coming back together as a particle. The white is completely separated from the black now. So what these fields are, the black and white grabbing a hold of each other and spinning like crazy. And the only one I can see that I can really see, I think I can see, is this one here. And hitting that, and they apparently create a spinning disk. That's all I can tell you, because I can see them where you can see all the little dots going all the way around each one of these. And that's what vibration is in the magnetic realm, is they push to shove, push to shove, push to shove. And that's why you get glow. And that's why you get those dots. All right, this is the one I'm talking about, the best shot I've got, showing the dots. You see all the little dots? And this is the thing that really interested me about this one, is that white particle there, right? That one, that white one. That shouldn't be doing that. Now this is like looking into the Venturi, having them coming out, and it appears that they must be, the white particles are hitting black ones here and turning into particles again, because they started this way. This is, I didn't realize this until just over a year or two ago. They started this way. All right, for this laser to punch through the gases that are in the air, it's going to push and excite their fields. Every one of these is a gas particle or a dust particle or something. And they're getting excited because they're getting pushed against. So they're creating a little tiny bit of glow, which the CMOS picks up. That's the key about the CMOS. Absolutely stunning how powerful it is. Now, particle wave duality, very simple. There is a tiny little particle in there, which is that 2 whites and 2 blacks, and it's going through the air with a field surrounding it because it's a magnet. It's magnetic. So you got a field out here, and there's nothing you can touch, but there's a field. And in the center is the particle. So the field has to push everything out of its way. They glow, this glows. Now, here's what I didn't understand. I'm looking at this and I can tell this is right when it starts to accelerate. Now let me show you something. As it accelerates, and really light can accelerate very quickly and very fast. All right, this one you got to think about for a minute. Remember I showed you that field that was just starting to accelerate. Remember this field here. And this is the front of the field. So it's just starting to punch through the air and force all these other fields to get out of the way. When they do, they glow a little bit. So we're seeing this as a glowy wave. And you can see it's bending back more. It's not like a round wave, which it should be. It's bending back this way because it's starting to accelerate. Now, in the acceleration phase, that field, just the particle, which remember I told you there's a particle in the field, and the field is around it, and it's coming, and all of a sudden it's going, and it just takes off like crazy. And the particle here hits the Venturi. A Venturi makes things accelerate. It's fluids. And water is a fluid. I mean, light is literally atomic vapor. It's a fluid. And as you make more and more of it, it turns into mass. Well, guess what? You look back here, you don't see any light fields. Right? Y'all don't see any. Do you? I don't see anything back here. I see this thing starting coming. Well, what happened here? What's this all about? And what's that all about? What's this and this and this and this and this? Where did those come from? Well, I can tell you exactly where they came from. This is gaining energy. It's gaining energy. And we did nothing to it other than shine it through a Venturi. It's got to be gaining energy. When it hit the Venturi, it was an explosion. The black particles can't get through. The white particles forcing themselves against each other's fields. The more a field forces into a field, the more glow you get. Look at these things glow. Well, why would they be glowing back here? All of a sudden just pop out of nowhere land. It's because the field reverse. You see this? This is a reverse electromotive force. It's a, and that's why you're seeing that field back there. I know you can see that. Over here on the other side, it's hitting these fields, but you didn't even know they were there. They're here. And they're coming through, but they're just not concussing enough to get excited. But pushing back at them, we can see these are almost identical to the Higgs fields. You see them? You see wave, and they're everywhere. So it's the explosion backwards, and this is literally a subatomic nuclear explosion. That's the particles that would be in your nucleus, and it's exploding, subatomic. Now, which means you shouldn't be able to get damaged by this. It comes right back into being light. Here, there's a spot where it starts to come back together, and it just creates this flow of fields, which are the Higgs fields. I agree with that. But they're coming through the air, you just don't even see them. they're starting from this side. When they get through coming out the other side, they come out just the same way they started in, or similar. It looks like to me. We're going to go look at Higgs fields right now. Don't forget, this is what they look like. They have a curve, and they have lines like that. So I think going in, they're basically the same as coming out. I mean, they sure look similar to me. I do have a lot of questions. I got to be honest with you. There's a lot of things that I would like to understand that I don't understand at the moment. But this was read, exact same frequency of light coming in. And it can change depending upon if it's getting crushed and so forth. And that one there, like I said, that one there interests me. But at 2012, this is what they were showing as Higgs fields. They could see them, but they were big chunks. They were big, chunky particles, and not like we had. They just had a whole batch of debris because they were hitting head on, and everything was scooting out. And it tries to take a circular form. All those particles will create these Higgs fields, but they're not, they're just matter that's trying to spin back together, I guess. I'm not sure exactly, to be honest with you, what's going on there. But I know light makes that spin. So I guess the even bigger chunks do too. All right, just so we stay on the right page here. The same particles. This is the green, this is the red, that's the blue. The blue goes too fast to see it as an actual photon. The red is quite simple, very easy to see it. That's what a photon is. And they actually spin on their axis. That's why you have upspin and downspin, depends on where the white particle is. That's my opinion on that. And you can see this is the same particle, and it's gone from an upspin to a downspin. They just go like that. And then, of course, when it hits the Venturi, it's gone. Now, up in here, you don't see anything. You don't see any light at all. These are starting to gain a little bit of energy because of the pushback. But coming forward, the laser is here, and it's not a photon, and you wouldn't see a photon until you hit here in this area, which means this light particle thinks it just hit a wall. There's so much pushback that it thinks it hit a wall. That's why when I showed you the other ones, they're brilliant. Look, these are light particles that are just coming forward, thinking everything's fine, having a nice day, and wham, they get slapped like this because they think they hit a wall. There's so much energy coming back. When the two of them meet, it's glowiness time. This is pretty top-end stuff, and it should be looked at for what it is. And they're starting to use the CMOS to see the same things, but those things grind slowly. I've been doing this for a long time, and I think I understand this stuff pretty well now. And I understand the particles gaining energy and the reverse energy, the explosion. I think we can get free energy out of here. You make something glow, the more glow it gets, the more energy you have. If you could funnel all that energy instead of just making one big splash instead of that, funnel it down into a receiver here that would suck that energy down to be able to use it, I think we might be able to get something out of this. Because we didn't do anything other than put the Venturi in the way of the laser. And so the laser has to accelerate. And when it does, it gets glowy. And the green is the same particle for the green. See? It's up and down spin, same thing. Same particle. And for the blue, it's the same thing too, only it's just too fast. It came in like this, it's slowing down. And by the time out here, you can see there's actually two particles within that single looking particle. But when it comes in, it's coming in fast, almost straight, and it's drifting over. Now, this to me indicates that it is right, the right-hand rule, because the particle's going that way. It's slowing down, and it's spinning this direction. And the reason I know it's spinning this direction is because it's taking longer to get around the circle. So it has to be coming this way. And I know it's going that way, and we can see visually that it's slowing down. And just so you can see, two of them coming through the same time at the same Venturi. Venturi can be straight, this tall, can be this tall. So the one's a little lower, a little higher, and you can see the green has much more energy. It pushes the red down. The red just, it's dim. That's pretty bright, and then when it comes back, it concusses again out here. And it's the same particle. They are. There is no difference. There's going to be no difference between a red, a blue, a green, a yellow, a pink, an orange. It doesn't matter. It's the speed that's spinning back. So if you have it spinning at this speed, coming back at you, it might be red. This might be a little more bright red, and this is turn into the green, and then up into the blues, and then you're really rocking. And that's exactly the way they show it. What I just showed you is this. I just showed you the same thing. Really stretched out, you're way down here, they're waves. But they're not waves, they're spin. And there, I can prove that. These spin. It's not that they go flapping like this. These are particles that spin. And first of all, you saw it with the blue. You can see it's spinning as it goes. And it is, in this case, it's slowing down as it goes. Well, they're going to slow down. It doesn't matter. When people say light doesn't slow down, that's just not right. It's not true. Light can slow down. It can speed up like a rocket ship. And anytime you pop the field to field, you get energy. This is energy. And that is the energy that developed here, not here. From here was a laser. Very inexpensive, and they don't use a whole lot of energy. And then from here is where the energy developed. Could that be free energy? Maybe. All right, this one perplexed me. On this side, there's not a single black ball that I can find. None. Only the white has come this way. You guys, I can see the black balls. You see those black balls coming that way. Now, are they spitting them? Well, they must be spitting them all out because they started as light. Light starts as the two blacks and the two whites. And as far as I'm concerned, all we got is white here. I can't see not a single one. And there is such a instantaneous bounce on this side. It's just, you can see it. Well, I think you can see it. You see how tight those lines are? Those are interference patterns, they call them. The whole thing just blows my mind. All this stuff going on out here, this big field here. This is, you can see it's dim compared to this. And the black parts are over here, and you don't see a whole lot of Higgs things going on over here. You see, I don't know. These are the kind of things that need a lot of attention. Somebody's got to look at this stuff. I've been looking at it for 12 years. And I think I understand a lot of it, but what if you had tin here? What if you had copper here? Are these involved in like ionization of ripping particles off of metals and things like that ripping these little particles off? Maybe they are. I don't know. But it would be nice to try the same experiments with a ton of different materials And we're not talking about a whole lot of money here. We're just talking about time. We spent years and years doing this. Okay, here we go. 2012, they discovered the Higgs particle.
In 2012, the announcement of the Higgs particle rocked the world, leading to unprecedented media coverage. A scientific discovery in which thousands of U.S. scientists participated was blasted across the globe by over 1,000 TV stations to more than 1 billion people. Time magazine declared it to be Particle of the Year, and Fabiola Giannotti, leader of one of the teams who found it, a runner-up for Person of the Year. Science, the flagship journal of the American Association of the Advancement of Science, named it Breakthrough of the Year. Scientifically speaking, this discovery was a really big deal. The data used to make this discovery was recorded at a large particle accelerator called the Large Hadron Collider, or LHC. Although the LHC is located at the CERN laboratory in Europe, the discovery was an international one. Scientists from across the globe were involved in all stages of this discovery. Over 6,000 researchers from institutions in over 60 countries are currently participating in the LHC experiments. Nearly 2,000 physicists from the United States contributed to this effort, and the U.S. provides more researchers than any other country. These scientists came from 96 U.S. universities and research facilities in 33 states, plus Puerto Rico. Like all LHC collaborators, institutions in the U.S. built equipment at their home facilities and shipped them to CERN, although the engineering skills and technical capabilities stayed in the States. U.S. scientists also helped operate the experiments and played a major role in analyzing the data that led to the discovery of the Higgs boson. There are examples where U.S. scientists have had a key impact. For instance, Dr. Joan Candela, a professor of physics at the University of California, Santa Barbara, was in the international spotlight on July 4, 2012, when he announced the discovery of the new particle as leader of a team of more than 3,000 scientists. The two detectors that independently discovered the Higgs particle, ATLAS and CMOS, can be thought of as huge digital cameras, larger than a 5-story building and weighing many thousands of tons. And they're not ordinary cameras. They have 100 million pixels each and can take 40 million pictures every second. By sifting through these pictures, scientists are better able to understand how the universe works. Fully a third of the cost of operating these detectors is borne by the U.S. Together, the U.S. Department of Energy and the National Science Foundation contributed about $165 million to the construction of each device. These agencies have a long history of funding fundamental research, resulting in technical payoffs, including such innovations as medical imaging and cancer treatment, material science, and high-performance computing. While the U.S. has supplied about 30% of the budget and manpower necessary to operate the LHC experiments, this number probably underestimates the impact of U.S. scientists on the LHC research program. Brookhaven National Lab provides the second largest group of physicists working on the ATLAS experiment, eclipsed only by CERN itself. The situation is similar in CMS, where Fermilab is the second biggest research group. The discovery of the Higgs boson is perhaps the best-known achievement of the LHC research program. However, the two experiments have made many other observations and measurements. Hundreds of American graduate students have written their PhD theses on research tied to the LHC experiments and have moved on into the country's technical workforce. America's strong commitment to fundamental research ensures that U.S. physicists will continue to play a central role in mankind's millennia-long effort to understand our universe.
That was written and presented by Dr. Don Lincoln. Now, I had interactions with Don. Anyway, I'd like to be part of this. I think I can show evidence that supports my side of the statement. The dipole electron flood theory works flawlessly, because it does.